All right, so the next method for volumes of revolution is the shell method. Let's take a look at what this looks like. So the shell method is taking layers like an onion, if you can imagine an onion. That's actually the perfect thought process for the shell method. It's taking layers one at a time. And so rather than those rotations being circles, right, where you're like slicing a circle, this is actually layers that are more like cylinders, right? It's cylindrical. And so the what we would want to do then with our integral, rather than integrating the area of a circle, we're going to integrate the surface area of a cylinder. And so that comes from 2 pi r times h. And so that's the kind of concept that we're looking at for this. So if we are rotating around the x-axis and we're using the shell method, then our function is in terms of y, because the height of those cylinders, you can see here by this rectangle, the height of the cylinders is going to be given by the function y, right, in terms of y. And then the uh, like the width or the radius of the cylinder, um, I'm sorry, I said that. No, that's right. The radius of the cylinder then is just going to be that y value. It's going to go from your axis of rotation up to where your function is at that point. And so um, what we have here for a rotation that is around the x-axis would be 2 pi times that radius, which is going to typically be just y if we're rotating around the x-axis and not some horizontal line, times your function in terms of y. Okay, and your bounds are going from c to d. Remember that your bounds would also have to be in terms of y. For the shell method around the y-axis, you can see that your rectangles here are upright. They're parallel to the y-axis, and so you're rotating it around this way. And so we look at the height of that rectangle being the function defined in terms of x. And then the radius of that rotation is going to be the x value. Okay, so here you would have 2 pi times the integral from a to b of x, provided that you're rotating around the x-axis, or I'm sorry, the y-axis and not some vertical line, times your function in terms of x. So let's take a look at a couple of examples for this one. Example number 1, we have the volume of a solid generated by revolving the region bounded by y equals 4x minus x squared and y equals 0. And this is being rotated around the line x equals 5. So from the get-go, we're going to look at something that's not rotated around um, the axis. Okay, so 4x minus x squared, it is good to note, it's good to have some knowledge of functions as they are. So I could quickly factor this out, right, into x times 4 minus x, which means that I have zeros at x equals 0 and x equals 4. So I know that these are the two intersection points for this function, and I know that this function is a parabola that's facing upside down, so it's going to go like this. Okay, I'm rotating this around the line x equals 5. So this is a vertical line, so that means I want this in terms of x. Yes. Sorry, I got myself messed up on that for a minute. So I want this in terms of x, which means my entire integral is going to be in terms of x. So I have 2 pi times the integral, and I need to know my bounds. So we can see that this function is going to go from 0 to 4. Remember, it's getting rotated around this line here. So this is going to give you sort of like a bunt shape, right? Once you rotate it around, it's going to have a hole in the middle. So we're going to have to do that inner minus outer concept to determine this. So I have the lower bound is 0, the upper bound is 4. And then I'm finding the, or setting up the surface area, right? The radius times the height. And so the radius is going to be the distance from this line 5 to the x value for across my interval. And so I'm going to have 5 minus x. So instead of just having an x for the radius, like I showed you on the previous slide, it's the distance from this line to the x value over that interval from 0 to 4. Okay? And then this is being multiplied times the height of those rectangles, which are defined by the function. So the function is 4x minus x squared. And here I've created the integral that needs to be solved. So I'm going to multiply this out, and I'm going to get 20x minus 9x squared plus x to the third. And then I'm going to antiderive this to get 10x squared minus 3x to the third plus x to the fourth over 4. And this is being evaluated from 0 to 4. So when I plug in 4, I get 160 minus 64 times 3, which is 192, plus 64. When I evaluate this at 0, all of those things are just going to come out to 0. So when I add these all up, I get 2 pi times 32, which is 64 pi. So the volume of this solid by rotating around that line is going to be 64 pi. Here in example 2, I have the volume of a solid generated by revolving the region bounded by y equals x squared and 4x minus x squared around the line x equals 2. So this one here, x squared, is a parabola with the vertex as 0. So it's going to go like that. And then 4x minus x squared, again, this one, it's the same one actually that we just did. It's going to have intercepts at 0 and 4, and so it's going to go like this. Thanks, forgive my drawing there. And so it's this shape here that is being revolved around the line x equals 2. So if you notice what I've shaded in here, this is going to be rotated and give us sort of like a bowl kind of shape with a fat center. That center is hollow. And so our rectangles now are going to be defined, or the height of the rectangles are going to be defined by the upper function minus the lower function. And so I've got 2 pi times the integral. I know that these intersect at 0, and their other intersection point I can test really quick by setting these equal to each other. 4 minus x squared is equal to x squared. So I have 4x minus 2x squared is equal to 0. Factor out a 2x, and I'm left with 2 minus x. So I know that these intersect at x equals 0 and at x equals 2. So this point here is 2. Now the radius of this rotation, again, is going to be 2 minus 2 minus x, because it's that distance for all of the x values on the integral. On the interval. And then the height of those rectangles that are being rotated around comes from the upper function, 4x minus x squared, minus the lower function, which is x squared. So now I'm doing some simplifying here. I get 2 minus x times 4x minus 2x squared. I need to distribute, so I get 8x minus 4 minus 8x squared minus 4, I'm sorry, minus 2x to the third. Then I'm going to calculate the antiderivative, so I get 4x squared minus 8x to the third over 3 minus x to the fourth over 2 after I've simplified that. And that gets evaluated from 0 to 2. So when I plug in 2, I get 16 minus 64 over 3 minus 8. When I plug in 0, I'm just going to get 0. And then here I have 8 minus 64 over 3. I'm sorry, this should be plus, plus, and plus. So this should be 24, which makes a lot more sense. So I don't have a negative volume. So 24 minus 64 over 3 is going to give me, what was that, 72 over 3 minus 64 is 8 over 3, so 16 pi over 3 is the volume for that one. Let's take a look at example 3 where we're using a calculator to evaluate this. So the first thing I want to do is look at this function on a graph. So I have the square root of 1 minus x cubed. 1 minus x to the third. Okay, this is being rotated around. Oh, it actually doesn't tell us. That's right, I was going to express that. So this is closed off by y equals 0 and x equals 0. What I want to point out is that this one here, so it's this little spot in here. And we can either do cylinders rotated. No, that's not right. Oh, it's rotated about the y-axis. That's what I was doing. I'm sorry. Rotated about the y-axis. What I was going to say was you can either do cylinders, right, the shell method, or you can apply the washer method here in terms of y. For the sake of time, I'm only going to do the shell method, but if you'd like to know how to do it with the washer method, or I would challenge you, I guess, to try and put it in terms of the washer method. So with the shell method, we've got the integral from 0 to 1 of x, which is the radius because it's being revolved around the y-axis, times my function, the square root of 1 minus x cubed. And so I'm just plugging this into a calculator to evaluate this. This is not something that I have to do by hand. So I have 2 pi times the integral, which is math option 9, from 0 to 1 of what I just wrote out. So x times the square root of 1 minus x cubed. The variable of integration is x. And that produces for me the answer of 2.322. If I wanted to do this as a disk method, that just means that I need to get my function in terms of y because I'm rotating around the y-axis. So let's do that real quick. I'm going to start by squaring both sides. I get y squared equals 1 minus x cubed. I want to get x by itself, so I'm subtracting 1 from both sides and then dividing by a negative. So I get 1 minus y squared, and then I take the cube root of that. And so the integral still from 0 to 1, but this time, remember the washer method is pi times the integral of the radius squared. So the radius is the cube root of 1 minus y squared squared dy. So we can use a calculator. I want to prove to you that this does work to use either method. So we've got pi times the integral from 0 to 1 of the radius, which is the cubed root. You can find the cubed root in the math menu, option 4. The cubed root of 1, we're going to use x because it doesn't actually matter what letter you put in there. And this is being squared. But we know that we have it in terms of y because we're using the washer method. And you can see here that it produces the same answer. So the reason that we would use one over the other is if you cannot get your function in terms of another variable and it's already set up for you in the disk or washer. But it is true that either method works to get you the same answer as long as you can write it correctly. Okay, if you want more work on the shell method, then you can go to page 474 in the textbook and pick your selection of problems that fall under 1 through 35 odd. If you need any extra help, please just reach out.